Thank you, everyone. Thanks for coming out. Really appreciate you joining us. So I thought I would start with something that seems like you've heard already, and that is that over time, organizations succeed based on their ability to change more rapidly and securely, Simon, than their competitors. All right, so what does that mean? Where do I point this thing? What that means, I guess, as William Deming might say, who was the father of quality control, right, is that organizations have to go through a process of planning for new systems and change, right, deploying those systems and change and collecting data to study the results, and then deciding finally whether to keep that change, right? And Deming was a big believer in decisions being made based on data, and one of my favorite quotes from him is, "In God we trust, all others bring data." So, believe it or not, this all started back in 1950, right, when Walter Shewhart had introduced what is called the PDSA cycle. And the PDSA cycle is something that Deming grabbed onto, and he took it eventually out to Toyota for manufacturing and quality processes. It was the idea of this plan, do, study, act cycle, where by planning we mean figuring out what you're going to be doing, by doing, of course, executing on that plan, and then by study, we mean collect data and figure out whether or not what you just did worked, right? And finally, if it did work, does it match your organization, does it match the mission, shall we continue? So we're deciding whether or not to continue with this. And then Deming figured out we should do that again, over and over again. So this is a cycle through which we all have to go all the time. And that's kind of a few things that I think Matt and Val had actually touched on, is the fact that we're always seeking to go faster, right, to improve. So that's what this PDSA cycle is all about, right? And the term we hear about quite frequently is agility, is our ability to get around this cycle as quickly as possible. So that's kind of the end game, is go around really fast and knock out every obstacle possible that will keep you from doing that. So PDSA today, what does that kind of mean? Right? This is based in 1950, mind you. So from a planning perspective, it means data analytics, collecting information, market opportunity, maybe customer input. From an execution or doing standpoint, it means architecture, designing some architecture, agile, scrum, service-oriented architecture, information as a service, containers maybe. Study, right, is about monitoring, collecting the logs, feedback, maybe data warehouses, other databases. Right? And then finally, acting or making a decision is based on the results of that study and maybe the organization's policies and mission. Right? So we're just going through a cycle that we have to do all the time. So what I'm going to focus on primarily right now is the do step. Right? So the change in product development process, architecture, infrastructure standardization, provisioning, and does any of this matter? Right? So let's start with the product dev process. But before we do that, we have a polling question. How many custom applications do you have in your organizations? It's gone up since yesterday. Wow, 100 plus in some cases. So you'll know what I'm talking about in a few minutes. Excellent, thank you. One more question. What development method do you most commonly use? Agile, waterfall, hybrid, or other? All right, big camp in Agile and hybrid. Thank you. So on that note, so I said I was going to drill down a little bit on the do step, right? So the first thing is that from a product development process, what does that look like? You know, there's a whole set of steps that we have to go through. Like I said earlier, in the PDSA cycle, you've got to kind of figure out what it is you're going to do. put together some architecture, start working on some preliminary design, start coding stuff, and then provision a VM. Test it, provision another one, maybe go through QA, deploy that into production and get some feedback. If something trips up in the middle of that, then we go back to the start, we start coding again, et cetera. So this is a whole process. And if we focus only on one thing, meaning in this case the blue parts, then we're kind of missing potentially a long pole in the tent. And so that's what we're going to kind of drill down on. So real quickly, just looking at the coding aspect, as you progress down the line, of course, every time we hit a bug of some sort, we end up incurring some cost. Later on in the process, it's more cost. Later on in the process, it's yet more, right? This is kind of standard stuff. You probably all realize that. And it's not so bad, but what happens if you've got more than one developer, more than one application, right? Then what happens? Right now, every single time we hit one of these bugs, or we have to go back in the process, and it doesn't really matter, it doesn't have to be software, by the way, it could be any kind of process, really. But every time we hit a rock in the road or a roadblock and have to go back, we're now stalling a bunch of developers. So our product deployment process actually looks a little bit more like this. A traffic jam, right? Every time a bug is discovered, everybody gets stuck, and we all have to stop and wait until things get fixed up on the road. But it's actually a little bit worse than this because in reality, it's kind of like a train wreck because everything's connected, right? Many times your applications are large, right? And if part of it doesn't work, the whole thing doesn't work. So the trains in the front the cars in the front can't continue forward. So what would happen if we could make this thing a little less coupled, right? What happens if the front trains could continue? Or the middle trains, once they get repaired, they could continue on their own, right? So this idea of decoupling and autonomy is something that might enable us to go faster and design a system that looks a little more like this, right? A loosely coupled autonomous system, which would allow all the parts to kind of continue going on without interruption, by and large. Of course, you're going to have dependencies, so some things will be impacted if something doesn't work. But overall, the entire system continues working, right? So how do we get there? How do we get this? Well, it starts actually with the architecture. And before we go into that, which of the following methodologies are you using in your environments? Is it test-driven development, continuous integration, or continuous deployment? And I guess we should have an other. Okay. Oh, a few more in the continuous integration, okay. Great, thank you. And one more question. Which tools do you use for source code management? Another Git fan, all right. All right, lots of others on that one, okay. So, about architecture, right? This is a typical application, right? You pull out one block and everything falls down, and that's kind of the problem. And if that happens, of course, it's an impediment to change. How do you change this thing, right? We're afraid of this domino effect that you change one thing and you cause 100 other things to fall apart, right? And unfortunately, in the example I'm going to give you, it's your turn to change the database. We have a problem with our database. And our database, the problem is that we've encoded this in such a way that we can only have 2,000 products, and we need to sell the iPhone 7. And so we're going to have to expand our inventory item list. And unfortunately, we can't. We have to make a change. And the way this thing works is, right now, all of these different apps are looking into the product database over there, and they're asking, they need to get information about the inventory, and they give it to the customers, maybe they give it to the finance department, et cetera. You might be plugging that into Salesforce.com, pulling in that information so the sales reps can know what inventory was sold to customers. We have a bunch of reports, we have a reporting database. All this stuff is all integrated, and if we make this change, we're going to affect all of that, unfortunately, right? But the way that we can make the change is by causing the table 101, for example, to point to a new one. We can make that change, right? Then everything would be good. The only problem is we can't make it because we'd have to change everything, right? And so why is that? It's because of data abstraction, right? We've lost this data abstraction. And in general, when we have this kind of direct database access in our applications, they create a coupling effect that causes us to slow down, right? We lose the ability to check for errors and all these other kinds of things. All that code has to be built into the actual applications themselves, right? So we need to kind of get away from that. Not to mention, if we don't have some kind of abstraction, we are locked into that particular database technology. We saw earlier that a lot of you are using, I guess, relational databases, which makes a lot of sense. But if you needed to shift for some reason, you might be locked in because of this. So databases are a very common place for integration, and because it's easy, really. And that's the plus of it. The bad thing is that it's easy now. It's just later that it's not so easy, right? So coupling is a really big issue. It slows us down. Right? It leads to lockstep releases. It slows down change. More coordination is required. You have to have more meetings. And loose coupling enables us to move much more quickly. So the more autonomy that we can create, the better. Right? Another issue that I'll touch on just briefly, I don't think it's really critical, but the idea of deduplicating things or in the code world, don't repeat yourself, can become a coupling issue or a scaling issue as well. So in the data world, it might be that everything is kind of resting on a point, and now you're forced into kind of vertical scaling. And as Val pointed out, I guess that won't be a problem in the future. But right now, we always have to work to get around it from a performance perspective. On a code perspective, we have to be really careful about sharing different libraries. You don't want something that one of your other services or applications to depend on a particular library, and then you've got to change it for other reasons, right? And now you're causing yet more code to change. So what we're looking for is ways to maybe duplicate things or not use those particular libraries so that we can scale, right? So just a little touch on that, because at the end of the day, what we're trying to do is break apart the application. Right? We need to be able to create a bunch of services and create a level of abstraction, right? And typically these days, the integration method of choice is REST over HTTP, but whatever it is, it has to provide some level of data abstraction in order for us to expand out, right? And so now, if we do that, if we introduce a new service, for example, so you can see from an architecture standpoint, I've lined up on the the second column from the left some services that abstract the information, so they create a layer between the applications and the database to allow us to make changes. And now all of a sudden the change doesn't look so daunting, right? We've only got to change inventory service, the production database, obviously, probably reporting database, and some reports. But we're not touching 100 other applications, right? So what we're able to do because of that is we gain parallelism. We can have people working on those other applications. We can have people working on that change that we needed to make because we want to sell the iPhone 7, right? So we can have a bunch of developers all working in multiple streams, right? And if we continue down this path, we can add more and more of it. And what this enables us to do is to increase our change rate, right? And eventually arrive at this nirvana, which is essentially a microservice architecture. So that's what microservice architecture is all about, is breaking up your components, maybe along geographic, maybe along team lines or organizational lines, or even business function lines. All right, so what do we get out of all this? We got increased autonomy, greatly reduced technology lock-in, lowered deployment risk, because as we break things apart, the changes inherently become smaller, lowered deployment risk, for the same reasons, increased speed and scalability, although we do end up with a lot more objects to manage. Hopefully some automation can save us there. So let's talk just a little bit about infrastructure standardization, right? So traditionally, the way things have run is that we have some kind of application that's been developed, which is very valuable and has certain capabilities, but it's not completely developed because we have to design infrastructure to support it, right? So now we're doing things on the infrastructure side and spending time there that isn't so valuable. And what this does is it creates additional coupling, right? So now you've got an application that's tied to particular infrastructure, right? Which is actually exactly the opposite of what you want to do. you want to have more flexibility. You want to define what your infrastructure capabilities are, and then based on that, we'll have the application guys go figure out how to make it work. Kind of makes sense if you think about it, right? Because why not have the software guys figure out how to make the software work? Seems obvious. All right, so what I've got here is a standardization quadrant that I borrowed from RPath, if you remember them back before they were purchased by SAS. So on the left-hand side, right, up here, right, we've got the platform standardization increasing upwards and the infrastructure standardization increasing to the right. Obviously, the idea is to move toward the right. Unfortunately, a lot of us find ourselves in the lower left-hand corner, which is that we have diverse platforms and we have diverse infrastructure, which basically means that we make snowflakes. And snowflakes are beautiful, right? But it's very hard to automate them. So if you do like snowflakes, I suggest you buy Ken's book, but don't turn your servers into them, right? And that's what this is all about. So why are snowflakes so bad, right? For those of you who like to ski, you probably don't think they're so bad, but certainly server snowflakes are bad. First of all, if you can't reproduce them, then you don't really have a process. You certainly don't have a reproducible process. And if you don't have a process, then you can't test it. And if you can't test it, you can't measure it. And as Peter Drucker would say, if you can't measure it, you can't improve it. And I'm sure Deming would agree. If you can't improve it, we can't go faster. And we were just talking about going faster, right? We want to go faster around our continuous process improvement cycle, right? So snowflakes keep us from doing that. So what we need to do is automate our build scripts, right? And those scripts, right, in order to get out of the snowflake business, we've got to have infrastructure build scripts. So those scripts have to be under source code control. I think we had a question about that earlier. Because if we do something wrong, we need to know why, and then we need to be able to fix it, right? And if we don't have the source code control, just like a developer, they don't know where to look for. They don't know what changed. And we need to know that, right? So in order to get reproducible results, we have to have the scripts to build our systems, and then we have to have them under source code control, right? So what we're doing is moving just a little bit further toward the right, right? And that we've now created infrastructure that at least it's standard enough that we can reproduce it. Okay, so what I would encourage you to do is think of your infrastructure as code, right? Destroy the works of art, or the snowflakes, implement build scripts and code version control for your build scripts, automate your testing, and then eventually your infrastructure itself becomes its own documentation, right? We're not as tied to runbooks and things like that. All right, so let's take a quick look at just kind of general deployment process. All right, so earlier, remember, we started here. It wasn't that big of a deal. It's kind of easy to manage, correct? But we have a new loosely coupled autonomous system, right, which means basically that we'll have more services and we'll be doing more frequent deployments of those systems. Right? So we really have this now, right? We've got many parallel streams of things going on at the same time. A lot more testing and QA. So earlier, I said, you know, we don't really need to focus on the VM provisioning per se, but now that we've got all these streams going on, we're building VMs, or at least application images anyway, much more frequently. So now this is becoming a problem again. So how do we solve this? Right? Let's take a look at a couple of deployment models that you're probably familiar with at least. One of them is many services going into one host, which hopefully most of you have drifted away from. Because of all it definitely reduces autonomy. And then of course you have all the problems with dependency, conflicts and things like that for whatever the various applications require. The other one is one service per host, which is actually very good, right? It gives lots of autonomy and allows you to have complete control of the configuration from an application perspective. And then something that's relatively new, right, is having one service per container, and then maybe having many containers on one host. So this kind of gives you the best of both worlds, not creating tons of hosts to manage, but giving you the isolation that you might have wanted in the other one, right? So if you think about the provisioning process here, we've got like infrastructure as a service basically generating maybe an OS image, and maybe we have some automation tool like Puppet to configure and build those systems, and then eventually arrive at an application instance, right? The problem with this process, it takes, let's say 10 minutes at a minimum. If you're doing hundreds of these things, 10 minutes actually adds up. So can we go faster? What do we need to do? We certainly don't want the person controlling these images to become the bottleneck, correct? So can we build more to the base images, like say application stuff? We need to understand how many technology stacks we have, maybe .NET or JVMs or whatever. How fast can these images be uploaded or moved around on the network? And maybe how many instances are needed, right? So how do we overcome some of these things? Can we go any faster? Well, actually, yeah. So if we build more, so what do we, the artifact that comes out of this process is really, rather than stopping at the OS image, we keep on building and we generate what I'll call an app image, right? We can deploy now app images and fire up those instances. Well, that's wonderful, and actually it's fairly fast, right? It only takes maybe 1 to 2 minutes. Our build is only 5 to 10, so at least launching our application instances are pretty fast, right? And for many purposes, it's probably good enough. But we can actually go faster, right? So how could we do that? Right? Well, the problem that we'd have to solve to go faster is that VMs are actually kind of large. I found this little survey from Veeam that was done a year and a half ago about where they found that the average VM size was 50 gigs or more. That's a lot of stuff to be moving around, if that's true, right? If they're 50 gig, they're surely taking at least 1 to 2 minutes to start up, right? So this actually starts to add up. You can see it's like getting slower and slower if that's true, right? So an application with many components could take quite a while to start up and start testing, which is a problem if we want to do lots of testing, as we just tried to do. All right, so how can you go faster? Well, this is where containers come in. Right? So if we go in, we actually, ironically, have to back up a little bit. And rather than now, rather than building the image to the extent that we did before, we have to actually take a little out now when we're talking about containers. We actually move back a little bit. Maybe we install Docker, right, on top of our OS. And then that's our image. We deploy those images, hundreds of them, for example. And all of a sudden, we have a platform in which we can put an app image, right, which is kind of the concept of Docker, right, or containers. So you have an application image which is now much smaller. So what we get out of this is we have an image that we're moving around that's actually much smaller than 50 gigabytes. It's a lot lower. I'll talk about that in a second. And because it's so small and we're not requiring all the OS information, we can launch these instances really rapidly. So we can fire them off like every few seconds, which helps us do testing. So what are containers, right? Containers are basically operating system virtualization, right? So rather than carrying around an operating system and launching that, we start from the operating system and then we build in containers or application containers inside that. So what we're doing is overcoming this 10 gigabyte or 50 gigabyte issue with the VMs, and we can fire these things up really rapidly and we can move them around. They offer a bit of isolation, of course. You can design it so you get one container per application, or one container per application. And of course, you can still even do, if you wanted, have one VM per container, which actually makes some sense in that you can deploy images around pretty quickly with that infrastructure. All right, so we've overcome the snail here in moving around a big golden image, as it were. So what's changed? We've increased autonomy, right? We've decreased coupling, as we talked about. Now we can deploy applications faster, right? But we've done this. We can do the instances faster as well, but we've done this at the cost of a lot more things, right? A lot more objects that we have to manage. But we should be able to do that because we have automation. Everything's the same, right? So we can probably manage this a lot more easily. So the question here is any of this stuff worth it, right? We just added a lot of complexity to our environment in a manner of speaking, right? We made some things a lot easier, but now we have a lot of interrelated things, many of them, right? It's not just one big module that you can deal with, right? So let's perform a little bit of a thought experiment, right? Imagine that you've got 10 changes that we have to make to our applications, I'll say in plural, or services in plural, right? And each change has a customer value of 1 unit. And in this case, I'll say 20% of the changes are valueless or fail. Right? Val touched on this idea, which is you want to fail fast. If you're going to fail, you want to fail fast so you can stop working on that, right? And then finally, the release rates for both of these architectures are exactly the same on average. What that means is, in the microservice example, we can release, let's say, 1 change per month. In the monolith situation, you can release 5 changes every 5 months. So if you do the math on that, I'm sure you'll figure out, as I did, that it's 1 change per month in both cases. So what does that look like? Well, month 5, here we go with monolithic release schedule, right? 5 months later, we release 5 changes, one of them fails, right? In 5 months, our customers just started getting value. 5 months later, we release the next one. Of course, we can start getting value after that, right? What does the microservice release schedule look like? Well, 1 month later, we start getting value. The next month, we introduce a new change and get value from that, and so on, right? We have the one that fails, we know within 1 month that it's going to fail, right? We're releasing every month, so we know right away, 1 month before the other guy knew it, we knew that this failed, right? So why don't we overlay these things and kind of take a look at it? So if you think about this value map, it looks a little bit like this, where the green is the microservices and the monolith architecture is the yellow. And so you can kind of see the green kind of poking out here. So what is that stuff? Well, Sean, this is for you. So you thought you were done with Algebra 2. We're back, right? So if you could imagine, and you knew I was going to turn this into a math problem, if you can imagine that F represents the microservice value offered, and G over time, and G is the monolithic application value offered over time, right? If you imagine those two things going on, right, then that would graph out to look a little bit like this. For those of you who have kids, Desmos is really cool. Put a plug in there for them. So what you have here is, again, you've got the green kind of poking out. So what is that stuff, right? Well, what that stuff is it's extra value, and in a different word, it's value time. Right? So you think of value, but there's also the concept of value time. And I might say that is energy. You probably know what that is because it's called kilowatt hours, right? Kilowatts times hours. So what is all that stuff? Well, in the business world, that's called cash. Right? It's actually cash. So what we have here is the difference between the cash of the microservice company, architecture company, versus the monolithic architecture company, right? And as you see, it accelerates. I mean, maybe I won't say that's accelerating because the change rate here is the same, but you see that it's growing, right? You see that the cache for the monolithic or for the microservice architecture is growing. It's actually worse than that relative to the monolithic architecture. It's worse because, as I just said a minute ago, because I started to say that it's accelerating, I didn't start accelerating it. I could have, right? Because the guys who are doing this microservice architecture, they're getting all this extra cash. So why can't they take some of that cash and invest in something to go yet faster? And if they do, we now have, what'd you say? Exponential growth, right? So not only do faster release cycles generate more cash, the extra cash is allowing us to invest more and offsets our costs. So what you want to do is really optimize for speed, not for cost necessarily in this world. So going back to the beginning, right, organizations succeed based on their ability to change, right? And as Fred Brooks, who is a systems architect or software architect and software engineer for IBM for a number of years, said, what, 40 years ago? As soon as one freezes a design, it becomes obsolete. So let's keep our systems changing. So for more information, I've listed here some good reading material if you would like. Or feel free to contact me or Sean Collins or some of our practice leads, Sean Collins, Dave Garraway, and Todd Gaske. Thank you.
Wow, that was tight. That was tight, Rob. Yeah, no, it's good. You did good. You did good. All right, before we take in questions, I'm gonna put a little pressure on you. Okay. What I'm gonna do is I'm gonna take a couple questions, and you're gonna decide out of everybody who asks a question, whoever has the best question is gonna win a shirt. I know it's a little pressure. All right. So we're gonna go with the first question. Raise your hand. See who's got a question first. We're gonna take the top question.
That's Simon. Simon's got a question.
Simon's got a question. Where's Simon at? Oh yeah, I see him. He's pausing.
Simon and I are still taking notes on the formulas and equations.
Is that what you're doing?
Just a couple there.
Yes. Let me look around here. Somebody's got to have a question here. For a t-shirt. First question gets a t-shirt. First hand up. Right over here, this man. Whoa, he's like a homeless Santa. How are you, sir? What? Yes, excellent. Good seeing you. Excellent. What is your name? See, I knew you guys enjoy that entertainment. All right, I had to wake him up a little bit. Thank you. John? Thank you for letting me pick on you a little bit, John. Excellent. That was perfect. I just got to get a little laugh tonight. All right, here you go.
Now I forgot the
I
question.
know, I threw you off, John.
Okay, I was looking at your equation there. You have a degree in mathematics.
Okay.
You were actually looking at the expected value, weren't you, as opposed to the, actually what it would be? Because statistically, that would averagely, or the average would work out on that one. Okay, but going back to the question.
Yes, go ahead, yes.
Okay, so if you're working with a group to design a program, and it can be broken into several parts, you're saying it's better to have each person working independently of each other, just so they have a common, way of interfacing with each other. Is that what you're saying at the end of the day? Or am I confusing everybody?
I guess, yeah, so I guess thinking about individuals versus team approach, I think that seemed to be a little bit, I don't know if you intended that, but the idea is generally that if you can allow people to work even as a team autonomously, it doesn't have to be an individual, as a team autonomously, so that they can make decisions about their area of influence, right, then that team can move faster than if they're tied to another team and what they're doing. Right, so if they depend on what somebody else is doing and they can't just at a click of a button make things happen, then they get slowed down. And so that's kind of what I'm saying here, is that it slows down the whole process.
It seems like you're saying we need, or if a team is going to work together, they have to agree on a certain way that, say, a person's writing program 1 or app 1 and somebody else app 2, they're going to have to agree on a common method for the two to communicate. And long as the person modifying one app keeps it within that structure, you're going to be working well.
Yeah.
But if you change the way they talk, you're in a whole lot of trouble.
Right, exactly. In fact, that's kind of the software architect's job, right, is to make sure that the method of communication between different modules or different services is defined, right? And so once you get that defined, it can evolve over time, but you need to have kind of that standard interface that at least abstracts the implementation details that the other services are using to provide their functions, right? So rather than, like my example was with like these applications actually knowing the fields within a table, right? That rather than doing that, you could use a REST interface, for example, to just grab the customer name or whatever, or not the inventory item or something like that, and then have someone else kind of make that database query for it, right? So you kind of separate that level, but exactly, you do need to define those interfaces that I talked about, and that's what a software architect would be doing. Right? That's kind of their job.
All right, do we have another question for Rob? I'm trying to look around here. Bum, bum, bum. Yes, sir. I'll bring you a mic. Hold on.
Rob, my question is, as organizations move this direction, what kind of changes do you typically see in org structures to operationalize this? And I mean, where do best-in-class organizations doing this end up from an org structure perspective?
Okay, that's a great one. I think Sean Collins is going to be answering that question probably, but I'll touch on a little bit, but I mean, some of this is sort of called DevOps, right? But it's the idea of eventually that team who's creating the code for that service owns end-to-end that service, right? So it's kind of the idea eventually that you would have that person getting the pager notifications, like the texts or whatever, right, about what's happening within their systems. And so those guys who wrote the code are able to then make the change so that they don't have to be notified anymore, as it were, right? So design the service so that it sustains whatever failure type caused the issue to begin with. So I see kind of I think is well documented, I guess, as well, just a shift in the responsibilities of the application people in general, that it extends far further than it has in the past, where you kind of turn it over to the operations team. So
Okay,
that's kind of one change, but I'm sure Sean's going to be touching on that later.
I have another question over here for you, Rob.
Yeah, actually, I did want to chime in a little bit on that. When you look at how organizations are structuring themselves, and DevOps is one paradigm to do this, there are plenty. The reality is you will probably, many organizations still have individuals who are part of an engineering team, are part of a software engineering team, but their specialty might be more in automation scripting or things of that sort, where that infrastructure as code comes into play. So while what we're seeing is the vanishing of specialization based on hardware skill set and more specialization based on software release capability and what you're adding to that value cycle. And I also wanted to comment, Rob, you should probably grab a copy of the Principia Mathematica, because you basically did Newton's proof for him there by shrinking errors.
You saw the error fix
Yeah,
there?
I mean,
Okay.
if you convert
Of course you did.
the lack of cache to error and shrinking that, that's basically calculus as we know it.
Afterwards, sir, come
purposely
up.
did
You
not-
deserve a shirt just for that. All right, so come up afterwards.
I
I'll give you one.
purposely did not put an integral in there, Sean.
Wow.
Jeez.
Yeah, you cut him deep, he says. Wow. All right, we have time for one last one. If somebody else wants to squeeze one in, let me look. Panning through the audio. Oh, yep, right back here.
Question regarding how, I came from a user arena before I joined Red8, and what I've seen in the development cycle for companies that don't have internal staff is they're outsourcing a lot of this. What happens with the outsourcing model is that they're splitting this up into numerous components, shipping that out to multiple outsourcers to do that, and your model disappears. How do you take back control of that? How do you work with companies to make sure that they understand what an outsourcer will and can do, and really try and drive that to the model that you're looking for?
Thoughts off the top of my head would be, you'd have to somehow figure out what get the architecture done by somebody, and then kind of, agree upon what that architecture is going to look like, and then have people build to that. I think you need to see that probably before you start having people do work.
You can always see Rob out in the lobby and around afterwards. You can shake his hand, say hi, take some pictures. All right, ladies and gentlemen, Rob Cotter, everybody. He was awesome. Give him a hand.
Thank you very much.